Hi, welcome to videomathlessons.com. Tonight we're going to do a Math 12 pre-calculus lesson. Our topic tonight is functions and graphs, and what we're going to be talking about is really finding the zeros or the roots of a polynomial function. This is part 2 for this. And part 1, we talked about a couple of these basic concepts that will help us do these problems. And we have Descartes' rule of signs, rational root theorem, the remainder theorem, synthetic division, and we're also going to use a little bit of old stuff, quadratic formula and completing the square to wrap things up. So you in Math 12 and pre-calculus, you actually learn a lot of things that are going to help you along in this course and in calculus. So let's get started here and let's jump into this. All right, so let's do f of x. So let's get a function going here. We got x cubed minus 11x squared plus 43x minus 65. And we'll start off by, let's talk about Descartes' rule of signs. So now Descartes' rule says, if for our original function, if you have a sign change, that's a possible positive root. Okay, so let's take a look here. So now if there's nothing in front, it starts out positive. So I got one sign change, two sign change, three sign change. So it says I have 3 positive roots. Or what if they're imaginary? Well, then that means you also have to take out the conjugate pairs. So you always take off pairs, subtract by 2's. So I could have 3 or 1 positive root. And let's finish out now. Descartes' rule says this. Well, listen, if you take your original function and you plug in negative x, that gives you the possible negative roots. So I'm going to plug in negative x right down the line here. Okay, some big numbers here, but this is okay. You got big calculator, big numbers. You actually don't even need a calculator to do this problem, but calculator will help us, and you'll see in a few minutes what we're going to use it for. All right, here we go. Now we learned about odd powers. You get the sign you start with. So negative x would be really just negative x cubed. That's going to be positive, so I'll have negative 11x squared. That gives me a negative times that to be negative 43x, and that's negative 65. Well, now we look for the sign changes, and I'm looking. They're all negative. So this has no sign changes. So I know there's 0 negative roots. So it's saying I'm going to have 3 or 1 positive roots, and there's definitely no negative roots. Well, that's nice. That's Descartes' rule. Now let's use the rational root theorem. Let's find out what these possible roots are. All right, and we're going to use the rational root theorem. And the rational root theorem says this. You're going to factor this back part. So now I'm going to break down 65. So I know it's 1 in 65. That's the easy ones you got to think about. And I got a 5 here, so I know 5 goes into it, and it'd be 5 times 13. And these are actually prime, so I know it's not going to go any, that's it. So you factor the back over factor the front, and there's a 1 in front if you don't see it, right? So we got plus minus 1. So without doing the Descartes, right, I know there's no negatives, but let's, you don't have to use that rule first. So we wouldn't know. So I'm just going to leave the negatives in here. So my possible roots would be plus minus 1, plus minus 65, plus minus 5, and plus minus 13. Now, from Descartes' rule, I know there's no negatives, but let's, this is if, that would be if they just said list the possible roots. Descartes' rule, rational root, done. Next one, remainder theorem. Now, the remainder theorem says, listen, if you plug in a number and the answer is whatever number you get left over, that's the remainder. And so if it's a root, I'm looking to get a 0 left over. Well, I could try plugging in a 1 here. I can plug in a 1 because 1's pretty easy. So I got 1 minus 11, so I'm at negative 10, plus 43, so I'm at positive 33 minus 65. Well, that doesn't work. And I could plug in negative 1. Now it's just getting a little trickier. So now, you know what? if you have the use of a calculator, now I could sit there and do this. I could do it. Probably not the best use of my time now. But if you have the use of a calculator, if you're allowed to use the calculator on this part, what you could do is graph it and take a look at what the root really is. So now I punch in the equation, I go to graph, and there's our function. Okay, notice odd function, right? It's going up and down like this. We can not even getting into all the end behavior stuff. So I look at this thing and I say, all right, oh, there's my root right there at 5. My root, I know for a fact, one of the roots is at 5. And by knowing, I've done, this doesn't curve around, this is it. There are no roots over here. Flat out, there's 0 negative roots. There's no roots over there. I know there's a root here. There could be some others down here, maybe at positive 65 or something like that, or positive 13, but, it'd have to flip-flop a little bit. I know that's not where they are, but let's keep going. Let's find them if we can't see them on the graph. All right, so remainder theorem or calculator cheat, that's fine. I'm using it as a tool, not a crutch. It's okay. Next one, synthetic. Well, now I know that 5 is it. Let's prove 5 is it. So I'm going to plug in 5. I'm going to do a synthetic division. And I'm going to write down the coefficients. And I'm going to do the problem. So now remember, when we do synthetic, you bring down the first number, multiply. So I got negative 6, multiply, you get negative 30, you get positive 13, you get positive 65, and I get 0. This number on the end is a remainder. So that tells me 5 was a root. And this is the new equation, that stuff right there. And it don't look like an equation yet because I didn't write it in equation form. So since this was a third degree polynomial to start with, I dropped down 1 degree. So this is going to be 1x squared minus 6x plus 13. That's this right there. And if they said to me at the beginning to write this in factored form, which they could have asked that as a different question. If I say factored form, f of x, and I know this plus 5 is a root, would have started out as x minus 5. That would be the factored form of this equation. And I could try to factor this back part, and I know it doesn't factor. So that would be the factored form. But you would try it, and it doesn't factor. So that's factored form. All right, we're almost there. Let me rewrite this now. So I got f of x equals, and what do we say? X minus 5. X minus 5. X squared minus 6x plus 13. Okay, that's the new factored form. I need to break this down. So now I have my roots, and I know 5 is a root. I'm going to break this down. Now, in the last part 1, we did quadratic formula, so let's, mix it up. Let's do completing the square. So let's do this one by completing the square. All right, so now I'm going to set this to 0 because the roots are at where y, or the f of x, equals 0. So this is like an easy complete the square. So I'll move over the 13. And it depends on who your teacher was, how they taught you, how you do it. I do it this way, where I just take half this middle term, which would be x minus 3, and I'm going to square it. Now, if I actually did square it, if I squared this 3, there should be a 9 here, which there isn't. So I'm going to put the 9 there. But you just don't go adding things to one side. So if it's an equation, keep it balanced. I add a 9 over here. So this gives me x minus 3 squared equals, and then you clean this mess up over here, and you get negative 4. Take the square root of both sides, so I get x minus 3 equals plus minus square root negative 4, which gives me plus minus 2i. Sorry about the pen. And finally, just move the negative 3 over. So my other roots, so I got one root here at 5, and then when I move this over, my other roots will be at 3 plus minus 2i. These are the roots to this polynomial. 1 real, 2 imaginary. Oh, that's it. Thank you very much. And if you have any questions, let me know, and we'll try to get some more videos up. Good night.